Early programming languages didn't offer much support for structuring complex programs. They gave you local variables and global variables and not much else. As programs became more complex, we needed to find a way to control which procedures could access which data. Procedures that willy-nilly made access to whatever data they get their hands on led to hard-to-find bugs. So we needed a more organized way, and we came up with the idea of bundling data and the associated procedures into an object with a well-defined interface. Early object-oriented programming languages started appearing in the 60s and 70s, and by the 90s, most programmers had adopted the object-oriented programming style because it was an efficient way to write and debug complex programming systems. Over the next 2 lectures, we're going to explore Python support for object-oriented programming. Python supports many different kinds of data. There's integers and floating point numbers and strings and lists and dictionaries, and you've been using these data structures as you've been writing your programs. From a Python point of view, each of these is an object. What, you ask, is an object? Well, objects have a type, and a particular object is said to be an instance of a type. So here's the type of all the objects above, and 1, 2, 3, 4 is an instance of type integer. Why we introduce the notion of types is that the behavior of an object is actually associated with the type. In other words, how integers work when you add them together, use the plus operator on them, that's actually different with integers than it is for floats or strings or lists. And so associated with each type is the information that's needed to say, how do I do a plus operation, for example? Associated with each object is an internal data representation. Some objects, like integers and floats and strings, are primitive. In other words, they hold some data and that's it. They don't have much in the way of internal structure. Other objects, like lists and dictionaries, are composite objects. They actually are a collection of other objects in the system, and they organize that collection in particularly convenient ways. Finally, each object has a set of procedures for interacting with the object. So for example, ints have a procedure for dealing with adding 2 ints together, and lists have a separate procedure for adding 2 lists together. In the case of lists, that means to concatenate them. Let's look at this more closely. So here's an example data object, the list 1, 2, 3, 4. So the Python type of that data object is list. There's an internal data representation, and we have some choices to make as an implementer of lists. For example, we could store the components of a list in a little sequential array of memory locations, each of which holds a pointer to an object, and associate with that array a particular length L of the list. So in our particular example, the length would be 4. And so long there's enough room in the array to store 4 elements, we're all set to go. Alternatively, we might choose to store a list as a linked list of individual cells. So we'd have a cell holding 1, and a cell holding 2, and a cell holding 3, and a cell holding 4, and the other half of each cell would be a pointer to the next cell. So a little daisy chain of these cells, one for each element of the list. Why would you choose one implementation over the other? Well, one of the considerations is what operations do you want to be efficient? For instance, suppose you wanted to take the length of a list. Well, in the top representation, the length is explicit. It's actually stored as an integer as part of the internal data. And when a user asks for the length of a list, just look up that integer and return it. Very quick, very efficient. If you ask for the length of a linked list, you'd actually have to go down that list counting as you go to count the number of cells that have been linked together. So the length operation is very inexpensive with the top representation and more expensive with the bottom representation. But now suppose that an important operation is inserting something at the beginning of a list. Well, with the array, we'd actually have to spend the time to copy all the elements of the array up one index, and then we'd have room to drop the new object at the beginning of the array. That is potentially an expensive operation. We actually have to move everything all around inside the internal data representation. With a linked list, we simply have to create a new cell and make the pointer in that first cell now point to the rest of the list. So inserting at the beginning of a list is actually very simple with the second representation. So there's a struggle implementers go through when they choose internal representations. They have to think about what they want to be efficient, and what things they want to be easy. The internal representation is meant to be private in the sense that users of the object shouldn't rely on any particular details. So for example, a user should use some sort of procedure that's associated with a list to get its length. It shouldn't assume it can reach in and grab an internal integer and simply use that as the length. And so correct behavior of the objects might be compromised if you actually make some assumptions about the internal data. Lists have a lot of procedures associated with them. There's procedures for indexing into a list or creating sublists, for concatenating or replicating the list. That's the plus and the star. We can ask many things about the list. We can find the minimum element. We can search for a particular element. We can ask for the length of the list. We can remove elements from the list, so forth and so on. So all the behaviors that are available to the programmer are really described by this list of procedures. And the procedures know about the internal data representation, but a user of lists should restrict themselves to the functionality provided by the operators and procedures. Okay, so let's pop up a level and talk about object-oriented programming in general. Object-oriented programming is sort of affectionately known as OOP. OOP. Okay, so first off, in an object-oriented programming view of the world, everything is an object and has a type. For example, the presentation that you're watching would be represented as an object, and somewhere inside of its internal representation would be a list of slide objects, one for each slide in the presentation. And each slide object would have internally perhaps a list of text boxes that represent each of the little groups of text on the slide, so forth and so on. So what we've done is to break a fairly complicated idea of a presentation down into this hierarchy of objects, which sort of makes it a little simpler to sort of think about how to actually organize the program that produces presentations. Objects are a data abstraction that encapsulate an internal representation and an interface for interacting with the object. So remember that the interface defines behaviors, for instance, length or display on screen or something like that, but the details are hidden inside the actual implementation that lies behind the interface. The way you interact with the object is simply to ask the appropriate piece of the interface to perform the desired operation. In Python, the interface is actually represented as a set of attributes, and there's data attributes and procedural attributes, which we give the special name to of methods. Now, some languages have support for data hiding, which prevents access to private attributes. So in implementing behavior, some of the attributes may be intended for public consumption, and other attributes may actually only be for the internal use of the implementation. So in some languages, you can declare some attributes private and others public. In Python, it doesn't have that distinction. So when you read a particular type of object, you will get a list of things that you're allowed to do, attributes you're allowed to use, and so you're just expected to play by the rules, even if you know something more about other attributes that might be available. Of course, one can create new instances of objects, either explicitly, and we'll show you how to do that in a minute, or often using literals. So when I typed in the text 1, 2, 3, 4, in my Python program, the Python interpreter knows how to take those characters and convert them into an integer object. And we can destroy objects. We can destroy them explicitly using the delete operation in Python, or we can just forget about them. We can sort of lose our handle to them. So if we say A equals some list, and then later on we say A equals some other list, that first list has sort of disappeared. In other words, it used to be the value of A, and that's how we got to it. But now that the value of A has changed, we can no longer get to that old list. So Python system will actually reclaim destroyed or inaccessible objects. It will go take that first list and return it back to its storage pool, since no one can actually access it anymore. And that process, quite appropriately, is called garbage collection. What are the advantages of object-oriented programming? Well, I'd suggest you actually Google for advantages of OOP. You'll find a bunch of very interesting articles that describe, why object-oriented programming has taken the programming world by storm. Here are some thoughts that I have. It provides a way of doing divide and conquer development. And what I can do is to go off and implement and test the behavior of each of my classes of objects individually. So I can think about when I'm, for instance, implementing presentation program, I can think of as a presentation as a collection of slides, and I'll think of making an actual slideshow as sort of going through and displaying each slide individually one at a time. And then each slide, when it's asked to display itself, might go through and say to each text box, please display yourself at your location in the screen. So what I can do is work sort of from the bottom up of implementing the display of text boxes, and then a display of slides, and finally the display of the entire presentation. And I can work on each of those behaviors separately, assuming that the other behaviors have been implemented correctly. So this increases the modularity and really reduces the complexity. The complexity of doing a slideshow from the presentation point of view really is as simple as individually presenting each of the slides in turn. So classes make it easy to reuse code. And in fact, many of the Python modules you've been using, really the way they deliver the functionality is they define new classes and all the methods and internal data that they have. And you basically interface with those classes to access the functionality implemented by the module. Each class has a separate namespace, so there's no collision on function names. So, I don't have to have a separate procedure called integer plus and list plus. I can basically look inside a class and say, please use your plus procedure, and that's completely a unique way of specifying which plus I mean. And finally, inheritance allows subclasses, which we'll meet in a minute, to refine or extend a selected subset of a superclass's behavior. What I'll be able to do is to say, look, I want to design a special MIT presentation, which is just like a normal presentation, but has a little MIT symbol in the bottom left-hand corner. So I can change one aspect of, for instance, the display routine to build that extra piece of functionality in, but I can inherit all the functionality that's inherent in the base presentation code to do slideshows, so forth and so on.